Okay. Welcome everyone to this IEEE ComSoc-SPS ISAC webinar series. And today we are very happy and honored to have Professor Marco Lops from University of Naples, Federico II, Italy, as our guest speaker. So I will first give a brief introduction of Professor Marco Lops. So Professor Lops received the Laureate and PhD degrees from Federico II University, Naples, Italy. He's currently a professor with the Department of Electrical and Information Technology, University of Naples, Federico II. And he has held multiple faculty positions in University of Naples, Federico, in the University of Cassino and the Southern Latin Cassino, Italy, and several visiting positions in the universities in the USA, like in the Minnesota, Columbia, and Connecticut, and Rice University and Princeton University. And he, from 2019 and 2015, he served the 2 terms in the Sensory and Multi-Channel Signal Processing Technical Committee. He was an associate editor for the Journal of Communications and Networks, actually Transactions on Information Theory, and actually Signal Processing Letters, actually TSP, and is currently a senior area editor of the actually TSP and AE for the actually TIT. And he was the co-recipient of multiple paper awards, including the 2040 Bison Paper Award for the Journal of Communications and Networks. And during the 2018 and 2020, he was selected as a distinguished lecturer for the Signal Processing Society. His main research interests lie in detection estimation with an emphasis on radar signal processing. Okay, so before we start our webinar, I would like to remind you again about our Q&A rules. So during the seminar, all the audiences will be muted. And please pay attention that do not annotate on your screen. And please type your questions and send them to the host and the co-host, and we will collect them. And during the Q&A, we will choose 3 to 5 questions to ask the speaker. And you might be named, and you're encouraged to ask a question by yourself. Okay, so without further ado, I will hand over to Marco. So Marco's screen is yours. I think you should unmute yourself. Sorry, Marco. I think you should unmute yourself. We cannot hear you. You should unmute yourself. Yeah.
Okay. Now you can hear me, no?
Yeah, we can hear you
okay.
Now. Yeah, perfect.
Okay, thank you, Fan, for this nice introduction. And thank you, everybody, for attending this webinar, which is titled Opportunistic Joint Sensing and Communication. Well, of course, the talk is about coexistence between 2 important fundamental functions, which are sensing and information transfer from a source to a destination. And this coexistence has been mandated by the need for larger and larger bandwidth for wireless networks, which has inevitably produced a shift of the carrier frequencies towards bandwidths which were traditionally assigned to sensing. From the research point of view, this has had a very visible advantage. Namely, it has brought 2 communities, radar community and the telecommunication community, who had not been talking, if not occasionally, to each other for decades, to interact rather deeply. And I would say that this is also been fostered by the development of some new technologies, primarily the widespread diffusion of millimeter wave communications. We will be seeing that this makes communication channels and radar channels rather similar, and also the development of massive MIMO architectures within the enormous amount of transmit antennas offered a lot of degrees of freedom, which has fostered integration between the 2 functions. Of course, the philosophies that have been so far proposed in order to realize this coexistence are diverse, and I couldn't say that there is a consensus on which one is the best. Everything depends on the external, even financial constraint. Indeed, we have systems which operate in spectral overlap with two active transmitters. And even in this category, we can find both cooperative system and uncoordinated transmission. In uncoordinated transmission, as you know, the communication and the radar transmitter do not negotiate how to share the common resource, whereby the attention is focused on interference mitigation, while more recently the philosophy of co-design has been put forth, wherein the communication codebook and the probing signal of the radar system are somehow co-designed so as to safeguard the performances of both systems. On a completely different philosophy relies the so-called dual function radar communications, the acronym DFRC, which I would say gave origin also to the acronym ISAC, Integrated Sensing and Communication, because here in DFRC, there is a unique platform and a transmit policy sophisticated enough to accommodate two different functions. I see a chart. Okay. Two different functions. And as a consequence, we have that we may have that in these DFRC systems, there might be a primary function acting as a host and a secondary function acting as a guest, or the two functions, communication and sensing, might have the same priority. Finally, there is, we find the so-called opportunistic architectures. Here we have that there is only one transmitter. It might be a communication transmitter or a radar transmitter, and the dual function is undertaken by exploiting the signal radiated by the primary transmitter as a signal of opportunity. So we have sensing through communication signals, typically at millimeter waves, or communications through radar probing signals. And I will be dealing with this kind of JSAC. I call that JSAC, Joint Signal and Communications, because it is a functional integration more than a hardware integration. Of course, this classification I offered here is kind of coarse, and if you want if you want to find a much more detailed taxonomy, you might refer to this review paper, Martone Amin, Digital Signal Processing, which came out in 2021. So let's see what is opportunistic joint signal and communication. As I was mentioning, we may refer to communication-enabled sensing, and this typically happens in millimeter wave communications, and it might be coordinated or not, and has been, in any case, explored rather deeply for applications like short-range sensing, short-range because, of course, the characteristic of the propagation channel at millimeter waves do not allow patrolling a large area. I would say that the most interesting applications have been on automotive. Then we have a radar-enabled communications, as we will be seeing afterwards that this might be cooperative or uncooperative. Let me start with millimeter wave communications, which is naturally an enabler of this joint sensing and communication. Why so? Well, we know that sub-6 gigahertz communications typically are subject to multipart, which was originally a foe, because in old generation wireless standards, the multipart was something to get rid of, while becoming a source of diversity and so a friend in more recent standard. Conversely, multipart in radar is always a foe. Multipart in radar is typically the reverberation that the surrounding environment generates onto the receiver, it typically results in an explosion of the false alarm rate, typically results in a masking of the useful targets. So it's definitely something to get rid of. Luckily enough, when we have millimeter wave communication, you know that millimeter wave communication must rely on line of sight channels, and line of sight is exactly the regime in which radar ideally operates, even though there are also radar which operates in non-line of sight. Also, we know that in millimeter wave communication, it is necessary to establish a good link, which means that there are frequent beam alignment and beam tracking algorithms, which somehow are akin to the corresponding search and training functions in radar. As a consequence, the idea has been put forth of using these millimeter wave communication signals as signals of opportunity, and to try to undertake sensing functions by collocating a radar receive chain in close proximity to the communication transmitter. Well, in this talk, I will be examining some major issues that arise when willing to undertake such sensing with millimeter wave transmissions, signals. The major point is that we do not have a key design tool that the radar engineers typically rely upon, which is waveform design. We have to try to do our sensing function by exploiting the transmitted signal, which is a communication signal, with no possibility of modifying it. On top of that, we have also some other side questions. First of all, the bandwidth at millimeter wave is typically in the order of several gigahertz, which means, as we will be shortly seeing, that the range resolution is in the order of decimeters, if not lower. Which means that this is a very good thing when it comes to the localization accuracy, but physical objects are typically range spread. So we will be examining a little bit more closely these, what are the problems arising from these opportunistic structures and what are possible solutions. So let me refresh, for those people who are not familiar with radar, some basics about radar detection. Let us consider a very simple radar system which transmits probing signal, which is a pulse train, wherein each pulse is unsophisticated, so ideally a rectangular pulse with a conveniently large duty cycle. And the period, the transmission period, is the pulse repetition time, PRT, which is tied to the maximum unambiguous distance of the controlled area. PRT typically is in the order of milliseconds, of fraction of milliseconds. And for example, 1 millisecond corresponds to a maximum unambiguous range in the order of 150 kilometers. So it might be also fraction of millisecond. Assume that there are targets which reflects back an echo of the impinging signal towards the transmitter. Of course, the delay at which these echoes are received uniquely determine the range of these targets. What do we typically do? Well, we do batched filtering, then we do energy detection, and when the detected energy exceeds a given detection threshold, we declare a target. Once you undertake matched filtering here, of course, you have that the range resolution, namely the accuracy at which a target may be ranged, is tied to the width of the autocorrelation function of the probing signal. And also the resolvability of close echo is tied to the width of this correlation. As far as the correlations remain separated, we can see these as two distinct objects, otherwise they overlap, they are not resolvable. As a consequence, it is obvious that our ideal waveform should be one whose correlation has a sharp peak around its maximum, a very low side lobes. And this explains why so much attention has been given to the issue of waveform design. Typically, we use sophisticated waveforms, namely waveform with a large duration bandwidth product, whose autocorrelation function has the desired or more or less the desired quasi-impulsive shape. Good. The performance, the basic performance of a radar, of an ideal radar, namely of a radar operating in the absence of interference and willing to detect a point target, is given in terms of false alarm probability and detection probability, which are tied to each other and to the average receiver signal to noise ratio by this very well-known receiver operating characteristic. This applies to the case that the target to be detected has a radar cross-section which fluctuates according to an exponential law, so a swirling one model. Good. Let's now consider what happens if we use a millimeter wave communication signal. And let's consider, for example, the 802.11 AD standard. This operates at 60 gigahertz and has a bandwidth of in the order of 1.8 gigahertz. Also, since I was mentioning, it is necessary to establish a good link between the transmitter and the access point. There is a phase which is called sector level sweep phase, wherein the transmitter scans the surrounding environment by sending a suitable signal in order to test the availability of good links. And this sector level sweep phase has been proposed as a possible phase wherein, on top of this searching function, an opportunistic sensing function may be undertaken. Namely, we may collocate a receiver in proximity to the communication transmitter and also getting information from this communication transmitter. And this receive chain could somehow elaborate the reflected echoes during the sector level sweep phase and come up with an image of the surrounding scene. Well, what is the problem here? The problem is that the signal transmitted during the SLS phase is a signal which very predefined format. There is a preamble, which is always the same. There is a header, and there is a payload. We might assume that the receiver, the radar receive chain, is fully aware of the whole transmitted signal because, of course, it has access to the transmitter. And, of course, we might choose a segment of this signal in order to do radar processing and to try to extract prospective targets. What's the problem? The problem is that if we try to use a conventional radar detector, namely a matched filter plus an energy detector plus a threshold, a fixed threshold to which we compare the detected energies, we have to consider what happens in terms of autocorrelation function. And we see that if we use the preamble only, which is the policy which has been proposed, because the preamble is invariant, and so we might simply use a filter matched to the preamble, we end up with having an autocorrelation function which is very far away from the ideal shape that we have mentioned before. We have an autocorrelation function with large subsidiary peaks. But even if we use the whole signal, namely if we were somehow available, elaborating a very long segment, or including random data of the transmitted signal, even in that case, the autocorrelation function would exhibit a number of periodicities tied to the presence of the preamble, and in any case would not be directly usable in order to undertake reliable detection. We would have an enormous amount of false alarm. We would have strong targets which would end up with masking weaker targets. So the problem is that we can use for sure these signals, but we have absolutely to show all of the complexity from the waveform design that is not a degree of freedom we can rely upon, onto the detection strategy. Well, let's see what are the difficulties that we are faced with. We are patrolling a region, so whatever object which produces a scattering towards the receiver is a target, which means that we are in a multi-target situation and that we do not have any clue on how many targets are around. So first of all, we have to define what a false alarm probability is. Well, typically, this is a multi-hypothesis testing problem. A safe way to define a false alarm probability is the probability to reject the hypothesis that no target is present on the scene, given that no target is present in the scene. But even so, we have the problem of multiple targets, masking strong target, masking weak targets, and an ambiguity function which is far away from, excuse me, not an ambiguity here, we are not doing Doppler processing, a correlation function which is very far away from the ideal shape. So a possible strategy is to borrow something from radar theory and something from communication theory. We can borrow, for example, the idea of constant false alarm rate tests from radar detection theory and the idea of sequential successive interference cancellation from multiple access communications with an orthogonal access. Let me explain a little bit in detail what I mean by this, I would say, strange marriage. Let us consider a very simple hypothesis testing problem. H1, we have that the received signal is something, how the subscript of the signal denotes the delay, so the distance from the receiver, plus noise against H0, which is just noise. And assume that the noise is normal with zero mean and covariance matrix CW. We define constant false alarm rate test, a test wherein neither the detection threshold nor the false alarm probability depend on the covariance matrix of the disturbance. Once we have this set up, we might imagine to do something like outlined here. Use CFAR test, any CFAR test. Detect the strongest echo by running a CFAR test designed around the disturbance, for example, white noise or the covariance matrix of the noise. Once you detect the first echo, add the detected target into the covariance matrix and rerun the CFAR test. And do this until the detection threshold is no longer exceeded. Namely, we have something like this. Here we have the signal coming from the radio frequency stage. We run a CFAR test repeatedly. When we detect a target, we update the covariance matrix that we give an input to the CFAR test by adding the detected signature. Of course, we can use any CFAR test. There are many CFAR tests with tests which are CFAR with respect to the covariance matrix of the disturbance. The simplest and most intuitive one is the so-called adaptive matched filter. This is simply a GLRT, generalized large ratio test. And this test statistic that you see here is independent under H0 of the covariance matrix of the disturbance, while this is the maximum likelihood estimate of the amplitude of the detected targets. Of course, this is how the algorithm would run. Let me show you what would happen in a realistic scenario wherein one selects exactly the parameters that are typical of the 802.11ad standard in terms of carrier frequency, symbol rate, bandwidth, kind of transmit pulse, and so on, as far as in terms of propagation model. First of all, let's have a qualitative look at what happens. Here, there are 7 randomly spread targets, all point-like, that's the key point, randomly spread targets, And this is the evolution of the algorithm of the test statistic, to be more precise, as the iterations proceed. You see that the red line is the detection threshold set once and for all. And you see that the first iteration, the strongest target is detected. Then its signature is eliminated by updating the covariance matrix of the disturbance according to the law shown here, okay, and so on, until nothing else exceeds the detection threshold. Well, this is, of course, a qualitative behavior. If you want to be a little bit more quantitative, let's fix the false alarm probability to 10 to minus 4, and let's choose a reference target in whose detectability we want to examine, comparing what happens if we use different strategies. The solid line is the detection performance for the target of interest when there are 6 more randomly spread targets in the controlled scene. And you see that since the red line is the performance that we would have if the target were isolated, well, this iteration seems to work pretty well in restoring the nominal performance. The blue line is instead what happens if we use a conventional energy detector without paying attention to the fact that we are in a multi-target situation. And of course, this may even outperform in terms of detection probabilities the iterative procedure. The problem is the false alarm rate. Of course, this has no control on the actual false alarm probability at which it operates, and the false alarm probability that you would have in case you use a pure matched filter is totally out of control. Of course, you see that here we have a double scale on the horizontal axis based on the propagation model we adopted here. We have here the range and here the corresponding average received signal to noise ratio. These are the localization performances. Well, there are families of curves. One is a little bit less precise because here the sampling rate is the nominal Nyquist rate. Here we have a bunch of curves which are a little bit more accurate because we do some oversampling and some interpolation. But the bottom line is that here we have the root mean square error in the range estimation measured in centimeters. Here we have usual, here the range, and here the average signal to noise ratio. And we see that even the localization accuracy of iterative procedures closely follows the one that we would have if we had an isolated target. While the matched filter, the pure matched filter with energy detection, well, it is reliable only if the signal to noise ratio is unreasonably large. Very soon, you see that the localization performance is absolutely unreliable. This seems, well, there are a lot of studies. I do not want to deal much longer on this issue. I would like to put forth some problems that opportunistic sensing through millimeter waves may may pose. All this theory that has been developed here has been developed assuming point-light targets. Well, point-light targets with a range resolution of decimeters or centimeters, well, are rarely are more the exception than the norm. And as a consequence, we must inevitably assume that a given a physical object yields returns on a number of consecutive cells. And there is no way, if we model, I mean, the scenario as a bunch of point targets, of having an idea whether these detections are from the same target or from different targets. The only way to decide, to make a decision about the nature of this detection is, of course, that of having multiple illuminations, so going multi-frame, namely illuminating the scene with multiple packets, not necessarily equally spaced in time, because in any case, the timing information is available at the receiver. So generate a range profile and then either run a data association procedure or do something else more sophisticated. The problem is that once we generate a range profile, namely an evolution of the range of this detection in order to undertake the association, we also generate a Doppler profile. So once we go multi-frame, we must be prepared to the fact that we have to run a detection estimation procedure with range and Doppler spread targets. There are several strategies that come up to my mind in order to solve this detection estimation problem. One possibility is to avoid to split up in detection and estimation. A detection estimation procedure we should be undertaken in one step. Well, there are, for example, the two techniques which immediately come to everybody's minds are the tech before detect. What is tech before detect? Tech before detect means that we try to form some tracks of prospective target in a suitably defined state space, associate to each part of this trellis a suitable metric, and declare only those tracks which exceed a given threshold. This is something similar to the Viterbi algorithm. Or we might also regard the received signals over multiple frames as subspace signals, and as a consequence try to detect the number of active subspaces in a large dictionary of potential states. I cannot be more detailed on this, but there is a number of sophisticated strategies that can be adopted for range spread target, from range and Doppler spread target. So this, I would say, completes what I was willing to communicate about communication-enabled sensing. And now I would like to talk a little bit about the dual paradigm of radar-enabled communications. Namely, we have a radar system which operates autonomously, does not modify its transmit policy in honor of a possible potential communication system, or does not modify or may modify. I'll be clearer. When we talk about radar-enabled communications, there are large families of sorry, the classifications in ISAC are really complicated. Two large families of systems. Indeed, recent research has been very much interested with the so-called information embedding in radar systems. What does it mean? A branch of dual function radar communication has studied the idea that this platform, this common platform, wherein the two functions are accommodated, has a primary radar function, but the transmit policy of the radar function is such that we can also transfer information from the platform to the destination. This has been done through waveform diversity, through careful choice of the side lobe of the antenna beam, and so on. But in this family, you see that the key point is that we always find systems wherein the radar transmitter operates with the communication and somehow treats the communication as a guest and adapts its transmit policy to the need for sustaining a communication link. Uncooperative systems, conversely, are those I will be talking about, are schemes wherein the radar transmitters transmit its probing signal with no concern about the need for communication, and is used as a signal of opportunity in order to transfer information from a source to a destination. There is a an early study on this in this domain, and it is a study which I think dates to nearly 10 years ago by Shannon Blunt and co-authors, where they consider a single radar pulse. So they focus on a single pulse repetition time of the radar and design under a covertness constraint, namely they assume that the communication should not be intercepted, a system to use the radar signal in order to transfer information from a transponder to a destination. And in particular, what they do is they rely on some cognition and hide the communication signal in a proper subspace of the clutter space. Here, I would like to take a different approach. Namely, I would like to talk about interpulse radar embedded communication. What is interpulse? We operate on a number of PRTs without any covertness constraint, because operating over a number of PRTs allows us to exploit an important characteristic of some types of clutter, namely the coherence time. Now, I'll try to be more specific. First of all, let me tell you that what we are doing here is we are trying to use the radar signal and the radar reverberation as ambient signal. And so we are in the field of ambient backscattered communications that we call ABCS. In ambient backscattered communications, we have some transmitters, which are in ABCS jargon are referred to as tag, use signals which are already present in order to transfer information. Always referring to the parlance used in ABCS literature, the transmitter is referred to as a tag, and the receiver is referred to as a reader. The constraint in this environment is that the tag be simple, namely that the tag does not even have a radio frequency chain. What the tag can do is to vary the amplitude of an incoming signal or vary its phase without any down conversion, resampling, and so on. So it is, in its simplest form, it is an antenna with a programmable impedance, but in a more modern world, let's say, it might be a passive reconfigurable intelligent surface. I don't know if everybody of you is familiar with these RIS. They are programmable mirrors which are able to collect rays and to focus them in a given point of the space. In both cases, these simple devices are nearly zero consumption. So either have a very, very low consumption or may be even able to harvest their own energy in idleness periods. The idea that I would like to talk about is to exploit as carrier signal that the tag may use exactly the fault, namely the clutter impinging the tag. And I'll try to illustrate how. Let us consider this very simple scheme. We have a radar somewhere here. We have a tag. The tag, of course, may be hit by a direct path from the radar if present, but will be for sure hit by the reverberation generated by the radar. We assume that the reverberation is due to ground clutter, namely is static or nearly so, namely produced by civil buildings, facilities, bushes, gardens, mountains, and so on. Remember that the radar emits a periodic signal, named any signal with period PRT, which hits periodically these reflectors, which scatters their reverberation towards the tag. Of course, the radar also generates a reverberation which will hit the reader. Since our idea is to use the clutter impinging on the tag as a carrier signal and to deliver this information generated by the tag to the reader, it's clear that in this scenario, the clutter is a friend here and is a foe here. Here is something that we want to exploit in order to deliver information. Here is something that we want to get rid of in order to decode the information. Let's see what can be done. Assume that we have ground clutter. Assume, then I will be back later on this point, that the coherence time of the ground clutter spans a given number, say capital L, of pulse repetition time of the radar. So a segment of given duration of the reverberation, this is the situation of the clutter at the tag. You see that a segment of given duration of this clutter signal repeats itself capital L times, where capital L, we have said that is the coherence time. Why? Because, of course, the electromagnetic characteristic of the reflector originating that clutter remains stationary during this coherence time. As a consequence, the clutter itself is a periodic signal when observed on conveniently short time interval, and a segment of given duration clutter repeats itself times, and as a consequence can be modulated by the coordinate of a code word of length capital L, thus forming a communication frame. The situation is like here. You see, assume that we have significant clutter returns here, 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 and here. We use segments of these in order to transmit the coordinates of as many code words. So we generate a number of parallel transmission channels, one sustaining its own data stream. The key point is that the signature offered by the clutter in each subchannel remains constant over the whole frame. So if we want to, this is the idea. We generate at the tag a number of parallel channels. Notice that we cannot assume that the receiver, which is the reader, has knowledge of the clutter at the tag or the clutter impinging on the reader itself. That might be assumed. We are not assuming it in this moment. As a consequence, what can we do? What can the reader do? Well, the reader can just undertake down conversion, some form of low-pass filtering, and then sampling. So let's focus on what happened on the first channel, which is this one, and we find it again here and here, and so on for all times. So after low-pass filtering, the reader takes a number of samples at the output of the low-pass filter in order to collect enough energy, thus undertaking what is called fast time sampling. And we can put each of these sampled version in each PRT on a row of a given matrix. So you realize that the matrix containing on the first row the K returns in the first PRT, in the Lth row the K samples in the Lth PRT of the first subchannel. We have as many of these matrices, of course, as are the subchannels we are activating. It's on this form. We have a communication signature, which is determined by the clutter impinging the tag, which is modulated by the code word. We assume that the code word is binary, because we remember that we have a constraint that the tag be simple. Then we have what? If you have a look at this scheme, we have that also the radar also generates a clutter which somehow hits the reader. So we have a signature, which is the clutter generated by the radar on the reader, but which is unmodulated. So if you look at this, due to the fact that during a period of time of PRT, the ground clutter remains stationary, this is a DC component, while this one is modulated by the code word. Okay, noise, whatever. So once we have this model, we have to decode this code word, trying to get in absent, without knowing the communication signature, because this is determined by the clutter at the tag, and without knowing the clutter generated by the radar to the reader. What do we do? As usual, GLRT. At the end of the day, we are able, the transmission rate is, of course, the logarithm of the cardinality of the code book employed at the reader, divided by the number, the frame length, namely the number of QRTs, or if you want, by the length itself of the code word. Is measured in bits per sub-channel use. The decoding strategy is very simple. It is an incoherent strategy because, of course, we are not assuming any channel state information. We don't know the signature. Notice that this strange operation of this strange projection operation is something that could be foreseen. Let's give a simpler look at this. This is a DC component. As a consequence, is entirely contained in an all-one monodimensional subspace of the signal space, which means that the GLRT cannot but get rid of this unknown disturbance by projecting the observations onto the orthogonal complement to the all-one subspace. At the end of the day, we are left with the problem of designing a code book in an L-dimensional space, but with one dimension, which is the dimension wherein the clutter generated by the radar on the reader lies, which cannot be used because it would be wasted energy. So we have an L-1 dimensional space. What do we do? Well, of course, the safest thing to do is to choose the code words as binary orthogonal. In particular, if L, the length of the frame, is a power of 2, we may choose these code words, these code words as columns of a Walsh-Hadamard matrix. Okay? And this is called orthogonal block encoding. Namely, we have a frame of length L, we modulate the clutter, the signature offered by the clutter at the tag through one out of the available orthogonal codes, and then we decode through an incoherent receiver. The performance is what we do expect. Namely, we have that depending on the model we use for the channel, we have more or less satisfactory performance. This set of curves are typical curves for error probability. You see that here the channel between the tag and the reader has been modeled as a Rice channel, and depending on the strength of the specular component, you have, of course, different performances. Of course, if you have a weak specular component, you have almost Rayleigh fading, which means that the performance is suffers a lot, while if you have a strong specular component, even at very moderate signal to noise ratio, you have a good error probability performance. The problem is the rate. You realize that the number L, the length of the frame, is limited by the coherence time of the clutter. We'll see that it is in the tens. the order of tens. And the number of orthogonal code words that we have is rather small. So the rate of this communication, of these sub-channels, is very low. How can we increase the rate? One might say, okay, do not limit yourself to orthogonal code words, use also non-orthogonal code words, increase the rate. The cost for this would be, of course, a dramatic impairment in the error probability. Why? Because non-orthogonal code words reduce the minimum distance, and so inevitably the error probability increases. There is an alternative though, and I just, outline the idea. Assume for a moment that we have a coherence time of the clutter which exceeds twice L. Well, namely, assume that for consecutive frames, two consecutive frames see the same clutter characteristic, namely the signature offered by the clutter to the tag and the signature impinging on the reader, the clutter signature, remain constant for two consecutive frames. Then we can encode. You can perform an orthogonal block encoding on each frame, and then we can add a differential encoding from frame to frame. Of course, this is a modulation scheme with memory, so there is a complication at the receiver. The receiver must operate on two consecutive frames, but the advantage is that the rate at this point is the sum of the rate of the orthogonal coding and the rate of the differential coding. More generally, if I don't have this longer coherent time, I may want to consider to split up a given frame in two halves and undertake orthogonal block encoding on each and differential encoding from frame to frame. Here is an idea of what I could get. Or assuming that the clutter remains constant for 8 PRT, so the frame length is 8. If I did block encoding only through orthogonal wave for code words, I would obtain this rate, because the maximum number of orthogonal codes I can use for L equal to 8 is L minus 1, namely 7. Conversely, if I split up in two halves the frame and I do orthogonal coding on the two half frames and the differential encoding from frame to frame, I get 0.64 bits per subchannel use. Of course, this is just an idea of how much our fantasy may be unchained in imagining modulation scheme. These are performance curves, which are rather, I would say, which are rather pretty much those that we would expect. Only one point, paradoxically, but not that paradoxically, what happens is that if for a given rate, I consider block encoding on the whole frame or block encoding on a half frame and differential encoding from frame to frame, I end up with having performance which is slightly superior. Why? Because I'm using more sophisticated modulation scheme with memory, and I'm accepting a complication at the receiver. Let me spend a word on the issue of the frame length. So, problem, I am assuming that the clutter coherence time is LPRT. But in real environment, what is the coherent time of ground clutter? Well, of course, it is tied to the extension of the Doppler spectrum of the ground clutter. And there have been a lot of studies about the width, about the Doppler bandwidth of ground clutter. This thought, which Maria Greco offered me, and is taken by Billingsley, gives measured Doppler spectrum for an S-band radar. S-band is particularly significant because it is around 3 gigahertz, which is pretty much in the band of many wireless services. And here you see that the Doppler bandwidth is in the order of 40 Hertz. So if we call delta FC the Doppler bandwidth, and if we assume that the radar operates at a pulse repetition frequency, the given PRF, of course, the maximum number of pulses in a frame of PRT so the maximum length of the code word, the maximum number of PRT within the clutter remains constant, is the ratio of the PRF over the Doppler bandwidth. Notice that PRF is, for example, 1 kilohertz, but typically PRF is much larger, because 1 kilohertz means that our radar has a maximum ambiguous range of 150 kilometers. There are many radars who look much closer. But even for 1 kilohertz, you see that in S-band, the number of pulses, so the length of the code word, is in the order of tens, so it's 25. Okay, these are, of course, numbers which are a little bit approximate. I would say that it is realistic that the frame length, namely the number of PRT wherein stationarity can be claimed, is in the order of several tens, depending, of course, on the PRF, depending, of course, on the bandwidth. In X bandwidth, we have a larger Doppler spread. There are a number of considerations that can be done. But in any case, it seems that this model, this approach, might be promising in situation where ground clutter is the dominant reverberation source. Of course, this is a preliminary set of preliminary results. First of all, let me say that all these results carry over to the case of multiple tags, whether we consider a sourced or an unsourced transmission. Sourced and unsourced, the difference is that in source transmission, we have different code books, namely not only the message is important, but also the sender, while in unsourced, the multiple access, we have that what is important is the message. So the tags might in principle share the same code book. And there are a number of assumptions that have been made. One overall, we have assumed that the tag reader channel, namely the channel linking the transmitter to the reader, is clean. Well, of course, we may choose where to place the reader and where to place the tag. But we have also assumed that there is no other source of interference. I just give you an idea why interference might be a problem here. When we consider this model, what are we saying? Here we do a modulation. So signal sent by the tag mimics a moving target with a measurable Doppler shift, while the clutter generated by the target, by the radar on the reader, of course, is unmodulated. So this is a kind of Doppler modulation. Of course, if there is proximity to the reader, a target, a moving target, this could have itself a measurable Doppler. So it could interfere with the signal transmitted by the tag and generate an interference channel. Also, here we have assumed no knowledge whatsoever about the clutter signature, whether the clutter was the clutter at the tag that we use as a carrier, or the clutter at the reader that is an interference to fight. But problem, what would be the effect of cognition? What if we could assume that the modulation format would sacrifice some rate in favor of enabling some channel state information acquisition? Or even more, what if we could consider the concept of commensality, namely the radar slightly modify its transmit policy in order to allow the communication system to undertake signature estimation, and so to go to coherent demodulation. And in general, what is the capacity of this system of parallel channels? Of course, capacity in this setup, wherein the length of the code was limited by the coherence length of the clutter, is not very significant. With capacity is an asymptotic measure, but in any case, it would give us an idea of what is the unbeatable limit in terms of rate that cannot be surpassed. Well, these are open questions, are open problems that I'm trying to look into, and that somehow motivates me to support these schemes, this scheme for future studies. Well, I think that I spoke for almost an hour, and so I think that my talk is over. Fan, you confirm that? I mean, it's an hour?
Yeah. So perfect timing.
So
Just 1 hour.
I think that it's, I mean, that is all for the moment. I'm open, of course, for questions and whatever questions you have. And I thank you for your attention, of course.
Okay, so thanks for your very wonderful and informative talk. We have several questions, and I think the first one is from Professor Andrew Giorgatti. So Professor Giorgatti, can you please ask the question? Hello? Are you online?
Can you hear me?
Yeah, we can hear you.
Andrea. Hi, Andrea.
Hi.
I didn't understand Giorgetti. Okay. Hi, Andrea.
Okay, fine. Yes, it's me. I was first of all, thank you very much for your presentation. It was very interesting, both part, the communication centric and the radar centric one. I saw a lot of things that I was not completely aware of, so it was quite informative. I have a general question that sometimes I ask to people that comes from the radar community, because I come from the communication, let me say, community. So usually the question is very simple. So usually in communication we have, you know very well. So let me say, standardize the channel model. So everyone can play with this channel model and can design a new system based on the characteristic of the channel, how dispersed it is, and so on. So what one of the difficulties that I'm facing is that in the sensing community or radar community, what I see, I have difficulties to find some kind of standardized model for, I don't know, extended target and clutter, especially, for example, in the urban environment. So I saw lots of literature in maritime radar, in airborne radar. I struggle to find some good models that I can play with, maybe even, let me say, not super refined model, but at least something for which I can play with, and I can compare my algorithms with the algorithm developed by someone else. So am I wrong? So is it true that
no, you are not wrong at all.
We are missing some.
You know that I am in between the two communities.
I know. This is why I'm asking.
The problem is exactly that. In communications, you have. You know that there is a transmitter, there is a receiver. You have full control of what you transmit, and the channel is either known or estimated or acquired and whatever. In radar, you don't even know if there is a channel. I'll be more clear. In radar, there is a prior uncertainty as to the presence of something. So what you can say is what would disturb your detection or tracking of the objects which are in the scene. But assuming that you have a channel linking a transmitter and a prospective target, would end up with optimizing everything with respect to that target located in that position, moving at that velocity, having that shape. And this is a problem. I must say that I'm happy that you asked this question, because I see a lot of papers from communication community about this ISAC and whatever. But someone who has some expertise in radar, some assumptions of a priori knowledge of the situation of the channel and whatever look a little bit unrealistic. I'll give you another example. You know that, for example, communication theorists are used to optimizing choosing the waveform so as to maximize the mutual information. Okay, typical. Okay. In radar, the maximization of the mutual information is not a good idea, because if you maximize the mutual information, you assume the target is there. So it is good if you know that something is somewhere, to maximize the mutual information in order to refine your estimation accuracy. But the mutual information does not account for the prior uncertainty as to the target present. And in fact, radar people who are into information theory maximize the Kullback-Leibler divergence, which encapsulate through the Chernoff-Stein lemma the prior uncertainty as to the target presence. So we have models, very good models for the reverberation, very good model for the disturbance, very good models for the jammer, very good model for the Doppler spread, for the Doppler history. But the channel for us is something that is a little bit unknown. What is a channel? I hope I answered your question.
No. I mean, you confirmed. I mean, the fact that I mean, it's an hard problem. Let me say, to have good model that can be standardized. Let me say, because we have so many uncertainties, so many variables in the system that is very hard to tackle the problem like in communication. So you confirmed what I was believing. So okay, that's fine. I mean, thank you very much.
Thank you, Andrea. I'll see you in Italy.
Yes.
Okay, thank you, Andrew, and thank you, Professor Lops. So we have another question from Yifeng Xiong, but he is now offline, and he asked me to ask on behalf of him.
Okay.
So he's asking, Professor Lops, from your presentation, especially in the parts of communication-enabled sensing, you are using the 0.118 waveform to do sensing. So that is the concept of opportunistic radar, right? So you have a extra radar receive chain, and it seems that there's a trade-off between the communication and sensing performance caused by the distribution of the transmitted signal, because in communication system, you're transmitting random signals to convey information, right? But that was not, tailored for sensing system or for the radar system. So when we do sensing or radar, they have reduced degrees of freedom, and meaning that their communication rate will be sacrificed, because we're using a relatively deterministic signal to do the communication. So in your radar-enabled communication system. So what do you think that we should do to strike a better or flexible trade-off, possibly by adjusting the distribution of the signal?
I'm not sure if I did understand. He's referring to the case of the FRC, not opportunistic. Right. Well, that is a good question, because in the FRC, you know probably better than I do, that there is the usual paradigm wherein there is a primary radar function and a communication function. And their randomness, for example, can be obtained through index modulation, for example. No, so you have a massive array, and you select the subset of antennas which radiate each time, and the message is encoded in what antenna you use. But this is, in any case, something which is wherein the communication system is a guest and the radar system is a host. I feel that a truly unified design, and for this, the paper, your very good review paper, the one on 6G, is very is when you study the trade-off when you do not do, you do not do any rigid resource allocation. You don't say in a truly advanced DFRC, this is for radar, this is for communication. You paradoxically mix things up and define some suitable merit functions and some suitable weight, so that the randomness, let me say, which is inherent in communications, and the determinism which is inherent in the radar, may be traded off wisely. This, I think, is but I mean, what I haven't seen much about that. Just, just recently, there is this unified design. So far, what has been more popular, the colleague is right, is a basic radar system which introduces randomness in some way. So I agree with him. So from my perspective, it's kind of open. I think that once again, the most difficult thing is to find suitable figure of merit to optimize. What are the figure of merit? There is always this contrast between the rate, which is something that we want to optimize, and multi-hypothesis testing. So how do we play with this? Okay, that's it.
Okay, thank you very much for your answer. So we still have several questions. So one question is from Faza Asim. So Faza, can you please unmute yourself?
What's that?
I am not sure if he's online. Hello, Faza, can you please unmute yourself? Are you online? It seems that he's not responding. So he's asking, how would you comment on the joint communication sensing and radars if we can simultaneously communicate and sense the user equipment and at the same time detect the target approaching the user equipment? Is that possible? And this,
no, I didn't understand. I'm sorry. How can you?
Let me put it in the chat so you can. Yeah. I think this is his question.
How would you comment on joint communication, sensing and radar? Sensing and radar is the same thing, no? As if we can simultaneously communicate and sense the user equipment. I fear I didn't understand.
Yeah, I think this is not so the second question is about
okay, the mmWave has high path loss, so the detection of the target should be at the base station, or they are separate. Okay. No, here I'm not talking about base station. Here we have the transmitter. May be, for example, a transmitter on a vehicle. This is not necessarily a base station. Also, in view of the fact that in millimeter waves, often there is no base station at all. So it is a transmitter which is located, for example, on a car, and which is searching a good link to an access point. And the receiver, the received chain, is co-located with the transmitter. So there is not necessarily a base station. That's my answer.
Okay, thank you, Professor Lops. So I think we have
I'm curious about the first question. I'm curious, but I can't understand it anyway.
Actually, me too. Me neither. Yeah.
Okay.
So the I think we have so Faza said he can mute. So okay. So can you unmute yourself, and you can explain the first question more clear? Hello?
Okay.
Okay, I think, okay, let's go ahead with the final question, I think. So we have the another question from Terry Guo. So Terry, can you please unmute yourself?
Hello, everyone.
Hi.
Yeah. Hi.
Hi, good to see you, Dr. Lops. I'm from a wireless communication community. So I'm interested in the communication infrastructure enabled sensing. So I have two related questions. First question is, communication signal has limited bandwidth and also limited power. So it's not like a radar signal. So it's hard to detect or estimate the things. So this is my first question. So do you have any opinion for that?
Yeah, in fact, may I show the slide? Have a look. I'm going to share the screen for a second, okay?
Okay.
Have a look at the slide where I show the performance. This performance, this is for millimeter wave signal. Look at the range we are talking about, 40 meters. You are right. And in fact, the key point is that when you consider this application, at least the ones I considered here, you are focusing on very short range sensing. You might even think of patrolling an indoor environment, but yes, for sure, you are not talking about 100 kilometers, for sure.
Yes.
And in fact, those performances have been derived by using exactly the parameters of the 802.11 AD, from the transmit power to the propagation channel, log normal shadowing, and so on. And as you can see, the range is in the order of tens of meters.
Right. Range, talking about indoor detection, also in communication system, there are many base stations, so we can take advantage of the number of, large number of transceivers. My second question is about sensing. Radar is mainly detect or estimate a target or several targets, but I think sensing is more broad, has more broad meaning. For instance, it's so hard to detect a lot of targets, right, simultaneously. But instead, maybe we don't have to count each target. Maybe we are interested at in some kind of sensing like density, for instance, density detection. So or other sensing functions.
Other?
Do you have any suggestion for that?
Excuse me, we are not interested in detecting all the targets, you said.
Yeah, I mean, sensing can be more broad,
for sure.
Right? Yeah.
For sure, the problem is, I agree with you. The problem is that once you receive back a given return, now it's not important whether it is from a communication signal, from a transmitted signal. You have no idea of what is there. So assume that you have a target of interest. Good. If this target of interest has around a number of scatterers, which could be target as well, the same dignity, what can happen inevitably is that these secondary, not of interest targets mask the target you are following. Because that would not happen if we could rely on sort of autocorrelation function, let me say so, which is an impulse. Namely, it resonates just on the target of interest, but this is not the case. So you have, even if you define a target of interest, you have to get rid of the rest. That is the key point in radar, in my opinion, to get rid of whatever else you're not interested in. While in communication, the problem is totally different. You are always interested in the data stream sent by a transmitter to a receiver. So everything is useful somehow.
Right. I guess
that's
maybe
my
we
idea.
Consider waveform design for optimal waveform design for sensing, not for target counting. I mean, radar signal is specifically to detect, separate the targets, right? But probably there are other metric for waveform design, giving
Of course, well, there is waveform diversity. Of course, the radar may use one particular waveform in search mode, different waveform in tracking mode.
Right.
So you may, of course, depends on the function you're undertaking. If you know that if a target has been detected and you are tracking it, you can change waveform, of course. So you go to waveform diversity. In general, when you do search, okay, of course, if you don't have clutter, for detection performance, what counts is the energy, doesn't count how you transmit it. One might think of adapting the waveform to the particular clutter scenario, but it's kind of dangerous. So I would say that what we can rely upon is the possibility of changing waveform based on the function we are doing, on the task we're doing.
I agree. Thank you.
No, we are welcome. Thank you.
ICC will be held in Italy. Maybe I can visit you next year.
Okay, definitely.
All right. Thank you.
Thanks a lot. Thank you for your interest.
Bye.
Okay, thanks, Terry. So, Marco, I have a final quick question for you. So, I have seen in your presentation that there's a technique to modulate information on the clutter, right?
Yeah.
Yeah. So there's a recent technique called OTFS modulation, orthogonal time frequency modulation, which is to modulate information in the delay Doppler domain. So you have symbols put in the delay Doppler domain. Can you comment on
Giuseppe Caire, yes.
Yeah.
I saw the paper by Giuseppe Caire, but I mean, I wouldn't say much on that because I have seen the OTFS used in ISAC, but once again, I remember papers wherein you assumed that the targets were there.
Ah, okay. So assuming the prior information.
Always there. So for sure, if you tell me that there is something, I can use the waveform which is best suited. If the problem is a joint detection estimation problem, I'm not sure that some results carry over. But without disputing the OTFS format, that's my point, my opinion.
Okay. Okay, thank you very much. Okay, so I think that'll be all for the questions. And we would like to thank you again, Marco, for your very wonderful talk. And I hope you enjoy the webinar.
Thank you all for attending this talk, this late time of the night, in China at least.
Yeah. We typically have this talk in the night to, to coordinate
to accommodate the rest of the world.
Right, exactly. Yeah.
Thank you anyway.
Thank you, Marco, for the wonderful talk. And we should be able to see you again in our next event, I guess.
Yeah, but you will be in Rome, no, for March, April.
Okay.
We will be there.
Okay.
We will be at okay.
GlobeCom. I'm not going to GlobeCom. So due to the travel restrictions.
So I will be on my own to deliver the speech. Okay.
Okay. See you, Marco.
Bye. Thank you all.
Bye. So bye, everybody.
Bye, everybody. Thank you.
Thank you. Bye.